Hi, everybody. This is the second part of our chapter 3, and this is on energy. Okay, the behavior of matter is driven by energy. Energy is a major component of our universe. Energy is the capacity to do work. Work is defined as the result of a force acting on a distance. The behavior of matter is driven by energy, and understanding energy is critical to understanding chemistry. The law of conservation of energy, similar to the law of conservation of mass, is that energy is conserved. Energy cannot be created or destroyed. The total amount of energy is constant. Energy can change from one form to another, and it can change from one object to another. But it can't be created out of nothing, and it can't vanish into nothing. There are different kinds of energy. Kinetic energy is the energy of motion. Okay, so that would be like a roller coaster rolling down a coaster, a track. Potential energy is the potential of energy that something has. So that would be like the roller coaster sitting at the top of the track, just waiting to fall down. There is electrical energy, thermal energy, and chemical energy. We are going to discuss all of these today. You have the units of energy. The SI unit of energy is joule. Another unit of energy that we're going to talk about is the calorie, the small calorie. And then there's the nutritional calorie, which is the large C, and kilowatts per hour. The average cost of residential electricity in the United States is about 12 cents per kilowatt hour. These are conversions that we're going to be using for our problems today, talking about energy. All right, so this problem is already mapped out for us, but we're going to talk about it and see what you guys think. So a candy bar contains 225 calories of nutritional energy. How many joules is that? All right, so when you're doing a problem, you always want to start with what you're given, 225 calories. And you want to look at, what am I trying to get? I'm trying to get joules. Well, I remember from that list of conversion factors given on the previous slide that I can convert large calories to small calories using this conversion here. And then once I'm in small calories, I have a conversion factor that goes from small calories to joules. Okay, so let's look at how we do that. All right, I'm going to start with what I'm given, 225 calories, and I'm going to use my pen. I'm going to convert my large calories to my small calories. I remember that there are 1,000 small calories in a calorie. Okay, so that makes my calories cancel. Now I'm in small calories, and I know that there's that conversion factor that converts small calories to joules. So I'm going to use that conversion factor. I want to make sure that my small calories are on the bottom so that they cancel, and my joules on top. Now I'm in the unit that I want, my joules, okay, and I can go ahead and multiply. So I have 225 times 1,000 times 4.184, and you want to make sure that you have it to the correct amount of significant figures, which would be 3 significant figures. You end up with 9.41 times 10 to the 5th. Okay. All right. Potential energy of a raised weight. So remember I was talking about the roller coaster. The potential energy of a roller coaster sitting at the top of a track is very high. As that roller coaster starts to roll down the track, its potential energy gets less and less and less. Same thing with the weight here. So I have the weight at the top. It has a lot of potential energy. As it falls, its potential energy becomes less and less and less. Chemical changes change potential energy. Okay, systems with high potential energy have a tendency to change in a way that lowers their potential energy. Objects or systems with high potential energy are very unstable, like that roller coaster sitting at the top of the track. Some substances such as molecules that compose TNT, which is trinitrotoluene, have a relatively high potential because energy is concentrated in them. TNT molecules undergo rapid chemical changes that lower their potential energy, which is why TNT is very explosive. All right, so let's talk about exothermic versus endothermic reaction. In an exothermic reaction, heat energy is released. Okay, so if I have a reaction that I'm doing in a test tube and my reaction is exothermic, my test tube will feel warm to the touch. Okay, that happens when you mix acids and bases together. My reaction vessel would feel warm. That is an exothermic reaction, and energy is being released. In that type of reaction, your energy of your reactants is greater than your energy of your products. In an endothermic reaction, energy is absorbed. Okay, so my reaction vessel would feel cold to the touch as my reaction is happening. The energy of my reactants is less than my energy of the products in an endothermic reaction. All right, atoms and molecules that compose matter are in constant random motion. They contain thermal energy. The temperature of a substance is the measure of its thermal energy. The hotter an object, the greater the amount of motion of the atoms and molecules that are in there, and the higher its temperature. All right, don't confuse temperature with heat. Heat, which has units of energy, is the transfer or exchange of thermal energy caused by the temperature difference. For example, when a piece of cold ice is dropped into a cup of warm water, heat, the thermal energy, is transferred from the water to the ice. Heat is a form of energy that transfers from a hot body to a cold body. I thought that made it just a little bit more clear. Now, temperature, by contrast, is a measure of the thermal energy of matter, not the exchange of thermal energy. Temperature is a degree of hotness or coldness of the body. All right, background of the Fahrenheit temperature scale. Fahrenheit temperature scale assigns 0 degrees Fahrenheit to the freezing point of concentrated saltwater solution and 96 degrees Fahrenheit to normal body temperature. On the Fahrenheit scale, water freezes at 32 degrees Fahrenheit and water boils at 212. Room temperature is about 72. All right, on the Celsius scale, water freezes at 0 degrees and it boils at 100 degrees. To me, that's a little easier to remember. Room temperature is about 22 degrees Celsius. The Kelvin scale avoids negative temperatures altogether by assigning 0 Kelvin to the coldest temperature possible. That is absolute zero. Absolute zero is the temperature where molecular motion will stop. All right, on the Kelvin scale, water freezes at 273 Kelvin and it boils at 373 Kelvin. Room temperature is at 295. So if you look at a comparison of the three scales, Fahrenheit degree is 5/9 the size of a Celsius degree, but you can look at this here. On the Fahrenheit scale, you have water boiling at 212, on the Celsius scale, 100, and on the Kelvin scale, 373.15. Then we have the freezing as well as absolute zero. Okay. You guys can convert between Fahrenheit and Celsius and Kelvin scales using these formulas. All right. You guys have some examples in the back of your chapter where you can try those. Kelvin is Celsius plus 273.15. That one's an easy one. And Celsius is on top, Fahrenheit minus 32 over 1.8. Now, when you guys are putting this into your calculator, you guys would want to have parentheses around this, right? Okay, all right. All right, temperature changes, heat capacity. Heat capacity is the quantity of heat required to change the temperature of a given amount of substance by 1 degrees Celsius. Okay? When the amount of the substance is expressed in grams, the heat capacity is called specific heat. Okay? And specific heat has the units of joules per gram degree Celsius. All right, so the larger the specific heat, the more heat that is required to raise the temperature. Okay, so we have a little table here of different specific heats of substances, and notice water has the greatest specific heat, and as you move up the metals, their specific heat gets less and less. So that means that it's a lot easier to raise the temperature 1 degree Celsius of lead than it is to copper, and then water is the most difficult. So I want you to think about boiling water in a pan. Okay, water does take a long time to heat up, but the pan does not take very much time, right? So the water definitely would heat up last. All right, let's go back there. Okay, relating heat energy to temperature changes. Gallium is a solid metal at room temperature, but melts at 29.9 degrees Celsius. If you hold gallium in your hand, it melts from your body heat. How much heat must 2.5 grams of gallium absorb from your hand to raise the temperature of gallium from 25 degrees Celsius to 29.9 degrees Celsius? The specific heat of gallium is this. All right, so this is what we're given. We are given our grams, okay? We are given our temperature change. We are given our specific heat, all right? So we need to use this problem here, okay? Um, this is our equation that we're going to use. Q is the heat that we're looking for. We have our mass, we have our specific heat, and we have our change in temperature. Okay, so we're going to start with our equation, Q, which is what we're looking for. Okay, we are given all of these things, and we just plug them into the formula. All right, so we have 2.5 grams, and now this is our specific heat, 0.372 joules per gram times degrees Celsius, and our grams cancel, okay? And now we multiply that times our change in temperature, which is 4.9 degrees, okay? Our degrees Celsius cancels. We're left with joules. They actually didn't put this on here, so that's a typo. And we multiply across. We have 2.5 times 0.372 times 4.9, and we end up with 4.557, but we know that we can only have two significant figures, so that is 4.6. All right, so we're going to try another problem here in the next video, and you also have some problems that you can try on your own. All right, I'll see you in the next one. Thanks.